Yeah, you can start.
Okay, so hello everyone. So I'll be talking about PCPs, which stands for Probabilistically Checkable Proofs. Okay, and what like the reason for this definition is basically like we want to study hardness of approximation. How hard is it to approximate solutions to certain problems? Okay, so like for example, like in the abstract I mentioned the three sat and three coloring problem. These are both problems that occur very naturally in a lot of places, and we would want to like solve them efficiently. But we think that we can't solve them because of the P is not equal to NP conjecture. And like the alternative is, can we approximate it? Can we find an approximate solution to the three sat or the three coloring problem? And this whole topic basically deals with this. So in this talk, like I'll first describe what a PCP system is, so, what a and then I'll describe some definitions, which basically are prerequisites to like all the theorems that we'll be discussing, and then we'll come to the PCP theorem, and which basically states that okay, this approximation is hard. So like we'll formulate this approximation problem in combinatorial terms, like properly using rigorous mathematics, and then we'll show that okay, this is NP hard. We'll basically reduce an NP complete problem to this problem, and like a bulk of the talk will be the proof, which is like a bit involved. I won't be able to cover the whole thing for sure. It's like I'll just give an outline of everything, and if you're interested you can like read later from the book. Like almost everything that I have taken is from that particular book, that Arora and Barak, 18th chapter, and a little bit from here and there, but yeah, it should be pretty clear after the talk if you start reading it. So let's start. So like the starting point would be NP. So we know that NP is basically a non-deterministic Turing machine. Like it's a class of languages for which there is a non-deterministic Turing machine, a polynomial time Turing machine, which is a verifier. This is an alternative definition to the non-deterministic one, that like we can basically, with an input instance, we give it a proof, and if the input instance belongs to our language, then there definitely exists a proof such that the verifier will accept it. And if the input does not belong to that particular language, then it is certain that for any proof that you give it, the verifier will not accept it. Okay, so like this is like if a problem is in NP, if a language is in NP, then this is the characteristics that it follows. Okay, and VPy is basically called the verifier, which has access to a particular proof that we pass it. And so now what we want to do is we basically want to extend this definition to into a probabilistic notion. So what we'll do is we'll say that we'll give this verifier certain additional powers. So this verifier now is probabilistic, and it has random access to the proof string. So here, like the verifier is a deterministic machine, okay, and it does not have random access to the proof, which means that like it reads the proof sequentially. So if pi is the proof, it's written on a tape, and like it has to read the proof sequentially. What we want now is that it is a randomized, it's a probabilistic machine. Basically, it can flip some coins and take some actions based on the outcome of those coins. And it has random access to a proof string, which means that it can just tell the proof that, okay, I want the ith, jth, and the kth bit. And the proof will only give those particular bits to our verifier. And like in the Turing machine setting, how this is done is like we add an additional tape, which is called the address tape, and the verifier just writes the address of the bits that it wants to access. And yeah, and the output is written on that particular tape, and the verifier can read it. Okay, so if we extend our verifier to have these capabilities, we'll now call that call this system of proof checking a probabilistically checkable proof, because the verifier is probabilistic and it is checking based on random access to the proof string. Okay, so like this is a pictorial representation. There's a proof pi, and certain number of queries the verifier can make to this proof and get results, and like it can take actions based on some random coins. We'll get to this. And the verifier can be like two types very naturally. First is the verifier which is non-adaptive, which asks for all the bit addresses at once. And the second type is an adaptive verifier, which can take its action, the next action, based on the response to the current actions. Like if I want to access ith, jth, and kth bit, I first access the ith bit. Based on that, I decide what the value of jth will be, and like so on. In non-adaptive setting, this is not the case. I just say that I want the ith, jth, and kth bit. I know what all these three numbers are, and in one shot, I have to ask, like I have to query the proof. Okay, and to rigorously define this notion, what we say is that the verifier is an RQ verifier, where R is some polynomial, some function, which tells us how many random bits that the verifier can use during its computation. And Qn is the number of queries that the verifier can make to the proof. Okay. And the verifier is polynomial time. And like we have to give certain bounds, like to what the verifier can and cannot do. So for that, we have like three definitions. One is efficiency, like the verifier should be efficient, then it should only use these many random coins and only make this many only make this many queries. Non-adaptive for now, we can generalize it to adaptive as well. And based on that, it has to define its outcome, yes or no. And completeness, that is, if the input X belongs to a particular language, then there definitely exists some proof for which the probability that the verifier accepts is 1. It's like with 100% certainty, if the correct proof is passed to the verifier, it will accept. And soundness, which basically says that if a wrong proof is passed to the verifier, the probability that the verifier accepts is at most half. Okay, so if we have these properties, then it's an RQ verifier. And yeah, so such a system of this kind of a verifier and this kind of a proof access is basically a PCP system. Okay, and so let's see why this is useful and like what else we can do with it. So consider the graph non-isomorphism problem, that we are given two graphs, G0 and G1. Okay, and we want to see if these graphs are isomorphic or not. Okay, so we will define a PCP poly n1 system for this particular problem. Okay, so what did we have? Poly n was Rn, so it can use polynomially many number of random bits to define, like to get to the result. And this was Qn, so this is the number of queries. So the PCP system can make only one query to the proof. Okay, in this case, we have to define what the proof will be and what the verifier will be doing. And then we have to show the correctness, that like basically we have to show all of these three properties. Okay, so the proof here is basically for, so G0 and G1, we are assuming they both have n nodes. And if they, by nodes, I mean vertices here. So they both have n vertices. And if they don't, we definitely know that there is these graphs are non-isomorphic, so like we can simply just give the answer. If they do have n nodes, what proof we require is that for every permutation of this n node graph, n vertex graph, either the graph will be isomorphic to G1, or it will be isomorphic to G2, or it will not be isomorphic to any of those. So if it is isomorphic to G0, we corresponding to that particular graph, so like we have a proof pi. Okay, and pi consists of multiple graphs, and for all graph, either it is a 0 or it is a 1. And if it is neither of these, then like we randomly assign it either a 0 or a 1 with half probability. Okay, and what the verifier will now do is, verifier, upon receiving this proof, the verifier will pick a random bit. Okay, it will either pick a 0 or 1, and it will pick a random permutation out of the permutation space for this particular graph, these graphs. Okay, it's like there are n vertices, it will pick a random permutation of these n vertices, and it will permute that particular graph. Like if the, assuming like the b is 0, it will permute G0 using that particular permutation, and it will query the resulting proof from the proof. Okay, so like it will query that particular bit from the proof, and the proof will reply either 0 or a 1. And if the graphs were isomorphic, sorry.
Aditya, I'm sorry, can you repeat what the proof looks like again? The proof.
Yeah, sure. Okay, so proof is basically, we have n vertices, right? So there's a graph with n vertices. And the proof is basically a string which consists of all permutations of these n vertices. Okay, and for each vertex, either this permutation is isomorphic to graph 0, or it is isomorphic to graph 1, or none of them. If it is like not isomorphic to either of these, we can just like randomly assign it a 0 or a 1. We will later show that this does not matter. Okay, so proof is basically for each permutation of the vertices, which graph is it isomorphic to? Is it isomorphic to G0 or is it isomorphic to G1? And what verifier did is it randomly picked a graph G0 or G1. It applied some permutation. It randomly picked some permutation, and it applied that particular permutation to the graph. Since all possible permutation of n vertices are there in the proof, the graph that the verifier gets after assigning this particular permutation also exists in that proof, right? And so the verifier basically queries that particular graph, which it gets after assigning the random permutation. Okay, so this proof will either say a 0 or a 1, which means that it is either isomorphic to 0 or a 1. Okay, and if the verifier had initially picked 0, and the proof also says that this after applying the permutation, the graph is isomorphic to 0, it basically rejects. It says that the graph is isomorphic, and if they are different, it accepts and says that the graph are not isomorphic. Okay, and yeah, so like the bounds is the last paragraph here. So clearly, if G0 is not isomorphic to G1, then there we can construct a proof. Okay, because we will know with certainty that the graph is G0, and like if the bit received is 0, then the graph is definitely G0. It cannot be anything else. Similarly, if it is 1, it can be it will receive 1, and it can be 1 and nothing else. And if it is isomorphic, then like in the worst case, we randomly applied, we randomly wrote either 0 or 1. So with probability half, it will either like give the wrong answer or the right answer. And we said that the soundness property should satisfy this condition, that the probability that for a wrong proof it accepts is at most half. So yeah, so like this is an example of a PCP system. Does anyone have any questions till now? I hope this was clear. Okay, I'll go ahead then. So yeah, this was an example of PCP system, like what kind of system we can construct for some particular kind of problem. But in this talk, we are interested in seeing how likely is it that we can approximate certain problems, right? So for that, we will go ahead and like define some other things, which are for now not.
Sorry, Aditya, again, one minute. Like the completeness. Sorry, yeah, the completeness part. So, say the verifier constructed a random permutation of one of the graphs G0 or G1, and
Yeah.
gave it, and then queried that permutation from the proof, right?
Yeah.
And if the proof bit turns out to be say 0, how does the verifier confirm that the graphs are non-isomorphic?
Okay, so verifier picks a graph at random, right? And
Right.
suppose that the graphs are not isomorphic.
Right.
And when the graphs are not isomorphic, whatever graph he picks out of these two, its permutation will be isomorphic to itself, but it will not be isomorphic to the other graph, right?
True. Yeah.
So the permutation that he has like applied, after applying that particular permutation, when he queries that particular bit, what happens is, if the graphs were not isomorphic, the verifier knows that with certainty it should receive a 0. If the proof is a valid proof, then with certainty it should receive a 0. Similarly, if the original graph was 1, with certainty it knows that it should receive a 1. And if the graphs were isomorphic, so like last case was the non-isomorphic case. So like we surely know that.
Yeah. 1 minute. So now suppose it queries and then it received so like say the original graph was the 0 graph. It created a permutation of that, and then it queried, and and the proof also gave it 0. Then how did it confirm like for sure the proof is valid?
No, so proof we are assuming is valid.
Oh yeah, okay, fine. If it is a valid proof, it should accept. Okay, sorry,
Yeah.
Okay, no, fine.
So,
Yeah. So if it's a
like,
fine,
yeah, there exists some proof pi such that if
okay.
the X input belongs to the language, it will accept with certainty. So we want to construct a valid proof, and this is the construction of the valid proof. For all permutations, apply these, add these bits to the answer.
Okay,
Okay.
yeah. Okay, yeah. Thanks.
So if you have a problem, like you have some random problem, some language L, and you want to construct a PCP system for that particular language, so what you need to do is exactly this. Like you need to follow this example. What you want to do is you want to define a proof, what your proof should look like. You want to define what your verifier is doing, and you have to give this bound that like there is some valid proof, that there is some proof that will give me the correct answer, and you have to like define some soundness parameter that your error is at max half. So for any problem that you have to design a PCP system, do this. Okay, so this was just an example. Yeah, so like for now, it just,
yeah. How do you say that for the graph problem that it is half? Again, sorry, I didn't understand. Like if G1 is isomorphic to G2, then the probability that any proof pi makes the verifier accept it at half. Why is this true?
Okay, so you got the non-isomorphic case, right? Like if the graphs are not, okay. So now if the graphs are isomorphic, then what happens? Okay, so now 0 and 1 are isomorphic, right? And since these are isomorphic, the random graph that he picks and the random permutation he applies, after that also, that the graph that you get is like isomorphic to both of these graphs. So it can get either a 0 or a 1, or it can get a random bit from this particular proof. Okay, and the probability of that happening is half. Like you added the bits at random, like that only, right? So if he receives a wrong bit from the proof, like if the proof says that they're not isomorphic, it basically accepts that it's not isomorphic. And we know that the error bound is at max half, because whatever like random thing that you added to the proof was with probability half. And like you can repeat and like get a better bound, like, boosting, right?
Yeah.
Yeah, so like you can go do it again and again and like get a better result also. But yeah. So for now, we'll just go through some definitions that will be necessary in the proof part. So like we want to rigorously define what a CSP is, constraint satisfaction problem. It is basically the generalization of SAT that you already probably know. So like we'll not spend a lot of time here. Here Q is a like arity and W is some alphabet. Okay, and these two belongs to the set of natural numbers, and this Q CSPW instance phi is a collection of functions, M functions, which are M constraints, and we want to satisfy these constraints when like using some inputs. Okay, so like what does it look like? Like there are like all of these functions are functions from the alphabet set to the like binary set 0, 1. And each function is like it's either satisfied or not satisfied. And what we want to do is we want to find an assignment out of these alphabet set which satisfies all or like most of these constraints. Okay, so like this is the rigorous definition of CSP, and like what this says is like each constraint phi, it depends on at most q locations of the input. Okay, so my input is n bit long. Okay, so like there are n things in my input, and all of these things belong to this particular set 0 to w minus 1, which is my alphabet. And q is the arity, which means that all of like any ith like constraint function should only depend on at most q places like of this input. So the input has n things, but each constraint individually cares only about q things in that input. Okay, like for all I, only q of the input matter and the others don't matter. Okay, and the whole like yeah, it's like that's it, I think. And we want to define this particular value here, value of phi, which is out of all the possible assignments that you can add to this particular constraint satisfaction problems, this particular function, what is the maximum fraction of the constraints that you can satisfy? Okay, so there are m constraints, and you define value of phi to be the maximum over like all possible inputs, the maximum fraction you can define. So if this is a SAT problem, what you want to know is what is the maximum fraction of clauses that you can satisfy. So like if this is a SAT problem, then each of this phi is basically a OR of some literals. And if it is a 3 SAT, then 3 is your Q, and your W is basically the binary function, the binary set 0, 1. It's because your inputs can either be a 0, 1. Okay. So this is called CSP. And we also want to define a problem which is called gap 3 SAT. Okay, so row gap 3 SAT. What this problem is basically, it's basically SAT only, but with an additional constraint that if phi is satisfiable, if the phi formula is satisfiable, phi is the CSP here. Okay, if this is satisfiable, then the answer is yes. If it is not satisfiable, like then there are two cases. The value that we defined in the previous slide here, the maximum fraction of clauses that are satisfied. If it is less than rho, then the input instance is a no instance. Otherwise, it can be yes or no. Like we don't care about those particular problems. Okay, so intuitively, what this is doing is, so like value can go from like 0 to 1. Okay, 0 to 1. So like it can either be perfectly satisfiable, that all the clauses are satisfied, or like it won't be possible, like perfectly unsat, but yeah, or only some fraction of the constraints will be satisfied. Okay, and we define the problem to be such that if it is satisfiable, then it is a yes instance if the value is 1, or if the value is less than rho, then it is a no instance of the problem. Okay, so this problem we'll call row 3 SAT, row gap SAT basically, and we'll use this later to do the proof of the PCP theorem. And okay, because we are not getting rigorously into the proof, so like we don't really need this, but like the intuitive idea of this thing, something called expander graph is, expander graph is basically a graph which has a lot of edges. Like that's how you can think of it. So like for now, don't go into the definition. The definition basically says that there's a parameter lambda, and like any random subset of the vertices of the graph that you pick, there should be a huge number of edges coming out of that particular set. Any random subset of edges that you can pick, there will be like a huge number of edges coming out of it, and that huge number is basically somehow quantified using this parameter lambda. So like, yeah, we don't need the rigorous definition because we're not really doing the proof. And Walsh-Hadamard code is basically like I hope most people here know what an error correcting code is. So Walsh-Hadamard code is basically one such encoding scheme. So there is some string X and you want to encode it somehow. Okay. And so what this encoding does is it goes from this X belongs to this particular set 0, 1 to the n, and it encodes this particular X to the space of 2 to the power n things. Basically, it basically expands the the encoding space. Okay, it's like yeah, we won't also go into the technicalities of this because we are not really doing the proof. Okay, so now we come to the PCP theorem. Before this, does anyone have any questions? Like it was just random definitions till now, but yeah, like this will all come together in the second part of the talk. So does anyone have any questions?
Not questions, just request. Can you like go a little slowly from now on?
Okay, sure.
You're talking too fast and it's like hard for me to follow.
Okay, yeah. Okay. Sure. Sorry. Nothing else? Okay, I'll continue then. So you can stop me at any point of time because now things will get a little bit yeah, tricky. So yeah, if you have any questions, just like keep asking. So we come to the PCP theorem. So like our problem was, can we approximate such problems? Like if there is, we have a 3 SAT instance, we know that we can't solve it. We probably can't solve it efficiently, assuming P is not equal to NP. Can we approximate it? The answer is no, we can't approximate it. Okay, because there is this PCP theorem which says that NP is equal to PCP log n and 1. And you remember what this is, right? Log n is basically R, the number of random bits that the system will use. Okay, so if the input length is n, the PCP system will use at most log n random bits. And this was Q, which was how many queries that how many queries can the PCP system make to the proof string. Okay, so PCP system receives a proof string, which can be of like very large length, but it can only make one query to the proof string. Okay, and one side of this equality is very easy to see. It's like this side is fairly simple to see. And why is that? So the reason for this is, think about how a PCP system will behave. So PCP system is basically a verifier, and it is using this many random bits, and it is making this many queries to the proof. Okay. Now, if it is using this many random bits, then what the I want to show that the PCP Rn Qn is basically a subset of n time. So what we want to do is we want to show that n time like non-deterministic Turing machine can basically simulate any PCP system, okay, with these constraints. So what will the n time Turing machine do is, this non-deterministic Turing machine can non-deterministically enumerate all of these random strings of length Rn, okay. So there are a bunch of strings of length Rn possible. Okay, and how many such strings are there? There are 2 to the power order of Rn strings, like exactly 2 to the power Rn strings here. But yeah, we are talking about upper bounds for now. Okay, so there are 2 to the power Rn strings, and the non-deterministic Turing machine can non-deterministically simulate all of these strings, and it can use Qn queries depending on that particular random string. Okay, and therefore in polynomial time, this machine can very easily simulate the PCP system. I hope this is clear. If not, I'll just go ahead again very briefly. So we know that the PCP system uses Rn length proof, Rn number of random bits. How many such strings can be there of length Rn? 2 to the power Rn, right? And since this machine is basically a non-deterministic machine, this machine can non-deterministically enumerate all of these 2 to the power Rn strings and check all of them. Like it can make queries based on all of these random strings, and it can perform every possible computation that the PCP system is performing. Therefore, we can simulate any PCP system with these constraints with a n-time machine or with these constraints. And here, what do we have? The constraints are that R is log n and Q is 1. Put those values here. What do we get? We get 2 to the power log n times 1, and which is basically n. So this is basically equal to NP. Okay, so this thing evaluates to NP if we put R is equals to log n and Q is equals to 1. Therefore, PCP of log n1 is basically a subset of NP. I hope this was clear. I'll stop after.
I don't get it. If it's a non-deterministic machine, why does it have the 2 power order Rn in the time? Like, wouldn't you try all of them like non-deterministic?
Yeah. It will do it in polynomial time. Like that's the whole point. So like it will efficiently simulate these many queries in polynomial time. Like the time that this will take to do this operation is of order n. That is why there is an order here. This is an abuse of notation, I know.
No, but that is not an abuse. I mean, okay, probably like I don't think computer scientists will complain about that. No, I mean, it's a non-deterministic machine, right? So like all the 2 power Rn possibilities, like they're like, aren't they non-deterministically checked? Like, I mean, like technically at the same time, like why would you have that in the complexity? You don't check like each of them sequentially, right?
Yeah, you don't check it sequentially, but you take the time equal to the time it takes to check one such string.
Yeah, to check one string, you only have like Qn, right? Into some poly. So I don't understand why the 2 power R.
The non-determinism is used for guessing the best certificate, and then you manually compute the probability of accepting that certificate by enumerating over every possible generated random string, of which there are 2 power Rn.
Wait, what? Can you repeat? I didn't understand anything.
Your voice is a bit like.
No, towards the end it became better, but I didn't understand.
Oh, actually, one minute, Aditya.
I mean, you
whatever
can.
is in the brackets, it's not time, right? What is the quantity that's in the bracket? It's number of.
It's proportional to the order of the amount of operations it takes. So it doesn't actually go through all, like it non-deterministically goes through, what Arjun was saying is it non-deterministically goes through all of these strings. Okay, but it goes through in the time equal to the time it takes it to go through one such string. But after that, there is some post computation, like it basically has to enumerate, right? Like, okay, this is a valid, this is accept, this is not accept, this is not accept. It has to do that. So, like those operations still exist. Am I right, Arjun?
I mean, as far as I understood, you want to show that n time this non-deterministic Turing machine that takes this much time can simulate. Wait, can you hear me properly?
Very noisy. It's extremely noisy.
Yeah.
Okay, how is it now?
Yeah, it's better.
Okay. So, yeah, you want to show that NDTM that takes this much time can like handle any language that the PCP on the LHS left-hand side can handle. So what you have to do is you have to find out whether there exists a proof that makes the PCP accept, and you have to find out whether the so as far as I understood, the non-deterministic Turing machines, like guessing the right certificate, is in terms of it guessing the certificate which will get accepted by the PCP if there exists one, and then it manually will compute the probability by trying all possible generated strings of like the random bits, which is like 2 power Rn bits.
Yeah, that was bad. Yeah. Okay. Yeah. Like I just saw this Rn randomness, and I thought non-determinism will just map to that, but I completely forgot that the proof selection is all the actual non-determinism that's used. Yeah. Fine. That's fine. Yeah. Yeah. Thank you.
Yeah. Thanks, Arjun. Anything else? Okay, so PCP theorem has another equivalent formulation, which is basically what the proof will use to show that it is NP-hard. Like the equivalent formulation is that there exists a arity Q and some gap rho, such that rho gap Q CSP is NP-hard. Okay, and this is like fairly easy to understand, and so I'll skip it. What I'll do is give this. Okay, this was good. So why are these two definitions equivalent? Basically, what you can do is, like for the PCP verifier V, you can think of this verifier as a CSP instance. Okay, and this verifier, which is basically equivalent somehow to the CSP instance, wants to get some input X and some proof pi. Okay, and this proof pi is equivalent to assignment of the variables that we do to the CSP. Okay, so like to reiterate, what we are trying to do is, like we had this formulation of NP, then we showed that one side of this equivalence is basically very easy. I mean, like it's not easy, but basically relatively simpler. And like this is the proof, okay, that the n-time n machine can basically simulate this. We want to show the other direction. We also want to show that NP is contained in PCP Rn Qn, PCP log n1. Okay, and to show that, we basically define another equivalent formulation, which was this. And right now, I'm just trying to intuitively explain why these two formulations are equal. There is a rigorous proof, which is these two slides, which I'm skipping for now. Okay, so the proof assignment is equivalent to the assignment of the variables. Okay, so on the left-hand side is the PCP, on the right-hand side is the CSP. And the length of the proof is equivalent to the number of variables. Okay, and like the complexity is directly in terms of this. And Q is the number of queries, and here Q is the arity. Okay, and there are the number of bits that the PCP system will use R, and And the log of the number of constraints maps to this. I'll explain this, why this happens in like 1 minute. There's the soundness parameter, which is basically that there should be a maximum threshold of error. And so here there is, we defined this row gap CSP with a threshold, right? If the value of val of phi is less than rho, only then it is a no instance. So the soundness parameter maps to this particular constraint, like this particular definition part, that the value should be less than rho. Okay. And yeah, so this thing that we want to prove now basically translates to that the fact that rho gap QCSP is NP hard. There exists some rho and Q for which it is NP hard. Okay, sorry. Yeah. And what did I say? I will explain later. Yeah, this logarithm of number of bits. So like to very quickly go over this, what you can do is like if you assume, okay, so like these are directly cutting from the book. Theorem 18.2 is basically the first definition here. Okay, and 18.3 is basically the second definition here. Okay. Like what it's doing is like, yeah, so you remember this, right? That the verifier V directly translates to the CSP instance. It is because of this. You can use this as your CSP instance. Okay, and you can enumerate this verifier over the random bits that you have. So that's how you can think of this as a CSP. And this number of random bits is equivalent to the logarithm of number of constraints, because the number of random bits you enumerate over all of these random bits. Okay, so like you can think of the verifier as one clause for one particular random string and combine it for all of these random strings, and you have something equivalent to a CSP instance, and you want to somehow satisfy it. Okay, so therefore these two definitions are equivalent. And yeah, like just read these two slides. It's easier. It's easy to follow. Okay. Yeah, so I'll skip it because of lack of time for now. So does anyone have any questions till now? If not, let's continue. Okay, so corollary of this fact is that there exists some rho such that if there's a polynomial time rho approximation algorithm for max 3 sat, then P is equals to NP. Okay, corollary of the theorem, which is the PCP theorem, that this particular problem is NP hard. Okay, and you can show that if there is a rho approximation algorithm for max 3 sat, then P is equals to NP. So basically, if you want to solve P is equal to or not equal to NP, you can basically come up with an approximation algorithm for one of these NP complete problems, which will do because of this particular theorem. Okay. I will assume that there are no questions for now and continue. Okay. So next, what we'll do is the proof of this particular theorem. We will do the other side of the proof. Like I'll give an overview, not the complete proof. Okay. So to do this, we want to define a new kind of reductions. So gap reducing reductions. Okay. So it suffices to give a polynomial time reduction which maps 3CNF to this, which is like fairly okay. So there is a if there is a input row that belongs to 3 sat. Wait. Oh shit! Sorry, these slides are messed up somehow. Okay, yeah, let's go to the proof. There is supposed to be something else here. I think I accidentally deleted that as well. Okay, so sorry for this mess up. Basically, what happened till now is we showed these equivalent definitions of the PCP theorem. We did one side of the proof, and now we'll go to the other side of the proof. And we showed this equivalence between these two definitions intuitively, not rigorously. And now we'll come to the proof of this PCP theorem. Okay, and so the idea of the proof is like really simple, and it's really elegant. Like a very simple idea is used to mathematically rigorously prove that, okay, you can do this particular translation. So what happens is, suppose you have this particular instance. you have a QCSP instance, row gap QCSP instance. Okay. And if you have a QCSP, then there are two cases. Either that CSP is satisfiable or it is not satisfiable. Okay, so if it is satisfiable, what is the value of phi? The value of phi, val phi is 1. Okay, because all of the constraints are satisfied. And if it is not satisfiable, then for any possible input that you can give to the CSP, for all of these inputs, there will be at least one clause, which might not be the same clause, but like for all of these inputs, there is some one clause which is not satisfied. Therefore, the CSP instance is not satisfied. And the proof leverages this very fact, okay, that if it is unsatisfiable, then the value of phi is less than equal to 1 minus 1 by m. So m is the number of clauses. Okay, and if the problem is not satisfiable, then there is at least one clause which is not satisfied in any assignment. Therefore, the value of phi, which was the maximization over all possible inputs, will be less than this 1 minus 1 by m. Okay. And what the proof does is it defines a reduction which basically expands this particular gap in case of unsatisfiability to a desired value. We want to expand this gap to rho. And this is what the proof does. It leverages the fact that there is at least this much gap in case of an unsatisfiability, and it stretches that gap to a desired value rho. Okay, so if like let that sink in, and like it's a very elegant idea, and the way it's done is also very interesting. Okay, so hence the gap problem. This is a generalization of 3-SAT and is NP hard. So we know that this is NP hard because we know that like 3-SAT is NP hard, and this is basically just the generalization. We did not change the problem. All we made was one simple observation that if it is unsatisfiable formula, then for any input, at least one clause is not satisfied. Okay. And yeah, this statement basically says this very thing, that we will expand this to a desired value, epsilon. But basically, this epsilon here is basically 1 minus rho. So define rho to be 1 minus epsilon. It's somehow easier to work with. Therefore, we define it this way instead of rho gap. So like these two are equivalent. Does everyone understand this? Is there a question here? If not, I'll continue. So the idea is you iteratively start expanding this particular gap to a desired value until epsilon is large enough such that epsilon is like close to some absolute constant. That absolute constant is the absolute constant that we defined in the problem instance itself. Okay. So we formalize this particular notion of this reduction, the reduction from 1 minus 1 by m to rho, using this reduction. So this is called complete linear blow-up reduction, CL reduction for short. Okay, and what this kind of reduction does is that there is a function f that maps any input CSP instance to another CSP instance in polynomial time, such that these two conditions are satisfied. Okay, if the input CSP instance was satisfiable, then the output CSP instance is also satisfiable. If the input CSP instance is not satisfiable, then the output CSP instance basically is not satisfiable with some change in the constraint, like in change in the gap. But the blow up in terms of constraint and the alphabet size is independent of m and n. So m is the number of constraints and like n is the input size. So the condition is that we want to blow up the gap rho, but we want to do it in such a manner that the blow up in the number of constraints is linear. It is independent of my input n. Okay, so here C and W can depend on the arity and the alphabet size of the input, like the input CSP instance phi. Okay, so you can think of this CL reduction as some black box. What this black box is receiving is some CSP instance phi, and it translates this into some f of phi. Okay, and the property that this satisfies is, first is if it is satisfiable, then f of I is satisfiable. If it is not satisfiable, then f of I is not satisfiable with an expansion in the gap. But also the condition is that if this has m number of clauses and n variables, this also has some linearly high number of clauses. This constant c is independent of n and m. C only depends on the arity q of the input function and the alphabet size w of the input function. Okay. And why do we want that? We want that because we want our problem not to blow up in the complexity. We just want to expand the gap. Okay. And there exists this is the PCP main lemma, which basically says that there exists a Q naught greater than 3 and an epsilon naught greater than 0, and a CL reduction F such that for every Q CSP instance on the binary alphabet set and every epsilon less than epsilon naught, we can transform the CSP instance into another CSP instance such that the value of phi is basically doubled. I mean, the error epsilon is basically doubled. Okay. And we can choose any value here, any blow up here. We choose one because of, we choose two because of convenience. Okay. And if we accept this main lemma, then it is easy to see that, like, if we assume that this is true, then PCP theorem is true. How? We can reduce NP hard problem Q naught CSP into this using this reduction. Okay. The idea is to use the CL reduction repeatedly and double this gap. We showed that the reduction doubles the gap, right? So double this gap in each iteration. If phi is the Q naught CSP instance with M constraints, then as observed before, if phi is satisfiable, then the value of phi is 1. Basically, value of psi is 1. Basically, it is also satisfiable. Otherwise, if value is like this, less than this, we can use gap amplification to amplify the gap. Okay, and we want the gap to be higher than some constant rho naught, right? And how many times do we have to do that? Like, how many times do we have to double this gap in each iteration to reach to a desired value? It's log m times. Okay, so if we double the value of epsilon in each iteration and apply this iteration log m number of times, we basically reach this particular value. The value of the output CSP instance will become this. Okay, and like, yeah, and we had this condition on the reduction that the blow up should be linear and it should only depend on the arity and the alphabet size and not on the input size. Therefore, it only blows up like polylogarithmically in n. Okay, and therefore, yeah, the PCP theorem is proved. Basically, we have expanded our gap from 1 minus 1 by m to a desired epsilon. And okay, so like the rest of the part is basically the proof of this very fact that like this PCP main lemma is true, that there is some Q naught and some epsilon naught, and there is a CL reduction such that you can do this, you can make this transformation. That will be what we'll be doing for the rest of this talk. So does anyone have any questions?
Wait, can you repeat that? What is?
What, am I audible?
Yeah. Like what you just said, can you just repeat it?
Oh, okay. So like, yeah, so if, so you guys, okay, so we know that if this PCP main lemma is true, then here I showed that the PCP theorem is true, right? The PCP main lemma basically implies the PCP theorem.
Yeah.
Okay. And for the rest of this talk, what we'll do is we'll basically show this particular main lemma. We'll show that this main lemma is true. What this main lemma is saying is that there exists a Q0 greater than 3 and an epsilon greater than 0, and a CL reduction F such that we can transform this Q0 CSP instance over the binary alphabet into another CSP instance such that the value of output is basically 2 times the value of input.
Okay.
So like this gap is basically doubled. This gap, yeah. And this is what I showed, that if you have this, if you have such a reduction, if you assume that the PCP main lemma is true, then here you can use this main lemma repeatedly. You can use this reduction repeatedly, log m number of times, to get to a desired precision. To get to a desired gap.
Right.
Okay. Yeah. So that's what I'm saying. Like for the rest of this, we'll just like prove this PCP main lemma only.
Okay.
So does anyone have any questions? Like,
what is CL reduction again?
CL is complete linear blow-up reduction. So we defined this particular reduction that, okay, so we know Turing reductions and like, yeah, so similarly we defined this kind of reduction, a reduction that follows these two properties. And then we said that there is a lemma, we call it the PCP main lemma, which basically says that there exists a CL reduction with this property. Okay. The CL reduction is basically like it should be complete. If it is satisfiable, output should be satisfiable, and it should blow up the like constraints only by a factor C, which is independent of the input size. It only depends on the arity and the alphabet size of the input CSP instance. Okay, so I should actually, okay, so in the proof till now, what we did is we basically said that like what the idea is that there is some gap. If it is unsatisfiable, then there is some gap. And what we want to do is we want to stretch this gap to a desired value, to a constant rho, such that our theorem holds. Okay, and we want to do it in polynomial time, and we want to do it such that the number of constraints are not blowing up dependent on the input size. To formalize this idea, we defined this reduction, CL reduction. And once we have this kind of a definition, we say that, okay, here is a lemma. If you believe in this lemma, then there exists a reduction which can do this, which can double the gap in each instance, in each iteration. And you can apply this multiple times to get to a desired value. And yeah, so like this is a technicality here, like this is minimum of 2 times epsilon naught, comma, this thing. Here it is doubling in each instance and we are applying it log m times, therefore it is 2 to the power log m. Okay, and m is basically 1 by m is basically the original epsilon. So the epsilon was 1 by m and like we applied it doubled it log m number of times, so it became 1 minus 2 to the power log m by m. And this exists because the main lemma says that this happens only when epsilon is less than epsilon naught. So there is some constant epsilon naught, which is basically a universal constant. If the this epsilon is less than epsilon naught, then it doubles. Otherwise, it does nothing. Otherwise, the value remains the same. Okay. So this technicality is because the definition says that there is the PCP theorem definition, if you remember, says that there is a universal constant such that this is NP hard. Okay. So yeah. Okay. So how do we prove the PCP main lemma? To prove this, we define 2 notions. One is gap amplification, and the second is alphabet reduction. Okay. And so this is the like the best part of the proof. Like this is the coolest part of the proof, and this is good because so before this proof, so this proof was given by Denur, the proof that I'm doing right now. It was given by Edith Denur in 2005, and before this there was another proof of the PCP theorem which was like very long and complicated, and yeah, and she gave this proof which was only dependent on which was only dependent on like combinatorics and like existing like well-built theories, and it was easier for people to follow. And yeah, it's like if you have studied complexity theory at any point of time, then you know that we have like a bunch of random complexity classes that give like small results. Like you might think that these complexity classes are defined just for one result. So like that is what happened. That is how the PCP theorem was proved, and then this proof came, which was basically easier to understand for a lot of people. So this proof basically this proof basically is divided into two sections. In the first section, we amplify the gap. So we increase the value of rho by some constant, and while doing this, our alphabet size increases. Okay, but in the output, we want the alphabet size to remain the same. Therefore, in the second step, we go ahead and reduce that alphabet size somehow. Okay. Gap amplification step is basically that says that for every L belonging to N, there exists a CL reduction called GL, such that for every CSP instance phi over binary alphabet that it receives, it outputs sigh, and sigh has arity 2, possibly over a non-binary alphabet set, and it satisfies this constraint that the value of phi is less than 1 minus epsilon. If it is less than 1 minus epsilon, then the value out in the output will be bounded by this 1 minus L times epsilon. Okay, for every epsilon less than this, so this will happen. So this is gap amplification. In this step, all we are doing is amplifying the gap, but the alphabet size can like explode. It can become non-binary. So in the second step, we want to reduce the alphabet size. Okay. So what the alphabet reduction step does is it says that there exists a constant Q0 and a CL reduction H, such that for every CSP instance phi, if phi had arity 2 over a possibly non-binary alphabet set, so the input CSP can be non-binary alphabet, can have non-binary alphabet, then it will output some CSP which has then arity Q0, which is over the binary alphabet set. Okay. And in doing so, the value can again decrease. So we want to increase the value, but like this step basically decreases the value. But the catch is we have control over this L. So whenever we define what our gap amplification step is, we want to define it in such a manner that this L is basically 6. So that when it decreases by 3, it like leaves out 2. So gap increases by 2. Okay, so we want this L to be 6. So whenever we define the gap amplification step, we have to control this parameters to get the desired value of increase. So each iteration applies a gap amplification and then an alphabet reduction. And at the end of these two, our rho increases by 2. So like this is the summary of what is happening. Okay, so we had an original CSP instance. We applied the arity was Q0, alphabet set was binary, and number of constraints were M. Okay, we applied gap amplification. The arity now became 2, and the alphabet size blew up, and the number of constraints blew up, but the value increased to a desired value. Okay, like basically the gap increased. And then we applied alphabet reduction because we want to get back to the binary alphabet set. So we did that again, and we got back to the desired place. And while doing so, our constraints increased by these constants C and C dash, but we defined C and C dash to be independent of N and M. C and C dash depend only on the input arity Q and the size of the input alphabet set, which is 2. So C dash and C only depend on Q0 and this W, which is 2 here. Okay, so we will apply this repeatedly and increase the gap in each iteration. And yeah, from here onwards, I'll just like give a brief overview of what this is exactly. Yeah, because I'm already at 1 hour. So does anyone have any questions till now? It's like, this is the whole heart of the proof. The heart of the proof is that there are two systems, like 2 algorithms that you can perform to any CSP instance to increase the gap while preserving the arity and the alphabet set, and by only blowing up the constraints linearly in M. So this is the heart of the proof. Does anyone have questions? Okay. Okay, if not, I'll continue. Okay, so gap amplification. Okay, like again, I won't go into like, just ignore all the text and try to follow me. I think. Okay. So gap amplification. Remember what we want to do in the gap amplification. We want to increase the value by some constant. Okay. So how do we do that? So this is like, there are multiple steps here. In the first step, you convert the given CSP into a CSP with the following properties: that the arity is Q, okay, and the constraint graph is D regular graph. So for any CSP, you can think of the constraints as a graph, basically, where your vertices are some parameters or the input, and your edges basically define what the constraints are, like what the connection between these variables is. Okay, and like whenever I'm talking about a graph, I'm basically talking about that constraint graph for the CSP. To give an example, if it is a 3-coloring problem, if the CSP is a 3-coloring problem, then the graph is basically the input graph, and the constraint is that 2 edges which lie on the same vertex should have different colors. Okay, if it is a like satisfiability problem, then the constraint graph is basically the graph that describes the binary relationship between the inputs. Okay, so this can be done in 2 steps. First is adding or splitting constraints such that my arity changes to 2. This is basically like just a technicality to preserve, like to get the value of the constant to a desired place. The second is that we want to change the constraint graph into a deregular graph, and we want to convert it into an expander. And to do that what the proof does is, you have a graph which is your constraint graph, take a random expander graph and add it to your original graph. Okay, so like you have some random graph here, okay, and it has some random edges, and take any expander graph. Expander is basically, to remind, it's a graph which basically any subset of vertices has a huge number of edges coming out of it. You have the adjacency matrix corresponding to this graph. You have the adjacency matrix corresponding to this graph. Like literally add these 2 adjacency matrix. You will get a graph which is an expander because you added something to an expander, which at the same time also has the constraints, because this graph actually defines some constraints, right? You have to cleverly pick the expander to not disrupt this. Okay. Yeah, so once you have done this, after this, you power the constraint graph. And what this means is you basically take the CSP instance, okay, and you want to transform the constraints to take values from a different alphabet set, and you want to transform the constraints such that they are over a like higher alphabet set, and the value is basically down. So what you do here is, I have a diagram here. So what you can do is, you basically take this phi t instance, okay, and like phi instance, and you transform this into phi such that the alphabet size is this, like something less, which is upper bounded by this particular value. W was your original alphabet size. D is the regularity of the constraint graph that you constructed in the last step, and T is the number of times you power that particular graph. So if you're talking about a 3-coloring problem, maybe, then like this power is like literally power the the adjacency matrix of that particular graph this many number of times, okay, T times. And when you do that, what will happen? Each of your entries will now correspond to a T length walk from one particular vertex to another particular vertex, okay. And when that happens, you want to preserve these things, right? You want to preserve these properties, that if phi was satisfiable, then phi to the power t should also be satisfiable. Okay, and if the value of epsilon was this much less than this, and it was this much, then you want your new value of epsilon to change by this much. And you can control this parameter t so that this basically is 6 times epsilon. Okay. And so like so the constants here are huge, but like it's still a constant, so it doesn't matter. And the last condition is that the phi t is computable in polynomial time in m and w to the power d to the power t. Okay, so so like the intuitive idea here is now after powering, each of your vertices correspond to some t length walk around this, right? So each of these vertices correspond to a t length walk, and and if you consider this ball of the length t plus t root t, then you can think that you can reach all of these vertices from this particular vertex, right? Because you have a path of this length. So you can, when you are trying to satisfy the constraints corresponding to this particular vertex, it will also contain the constraints from all of these vertex, because like remember that you have powered the graph now, like you have powered the matrix now. Okay, so when you try to satisfy a particular constraint, this basically consists of a combination of constraints, right? Like now psi t basically takes an input which belongs to this alphabet set, and it is a d to the power 5t tuple. Okay, so each of the vertex, when you try to satisfy it, you are basically adding constraints to some other vertex as well. Okay, and when you like this is how an increase in the number of constraint happens, and like this is how the value of like the parameter also increases. Yeah, I think I have to stop soon. Like. Anil, do I have to stop like real soon?
I mean, yeah, it's been 1 hour, 10 minutes. But yeah, like you can probably do a little more if you want.
Okay, sure. Because like this explanation will take some like
Maybe like skip the explanation.
I'll skip the explanation. I think.
Explain like if there's anything else, any other important details or something relevant.
Yeah, so like if you are interested in this, basically you can read the book. So like I have tried to cover all the portions which after you have like listened to this or went through this presentation, when you read the book, you will understand it like a little bit easier. I've tried to make it that way. I know that like in this talk, I won't be able to finish it anyways. Okay, so yeah, that is it. So like the important ideas of the proof is this only, that like you have to somehow change your CSP in these steps. And like the technicality here was that you power your graph, constraint graph, and when you do that, you get some new constraints. And how are these new constraints coming? Because you have powered the adjacency matrix, you have powered the constraint graph, all of your like when you try to satisfy one particular value, y here is the input to the new graph now, then you try to add some assignment to this particular constraint, then you are basically imposing constraints on other vertices as well, because like all the vertices that were reachable from the initial vertex, you are imposing some constraints on all of these. And the satisfiability or non-satisfiability of these new constraints is defined in the next slide. So like there is some, so like this is defined here, which I won't go over. Okay, and so now you have additional constraints, and you have a higher gap here because of this. So and okay, it's like I'll just quickly glance over alphabet reduction. What does this do? Okay, I won't actually. I won't be able to do it quickly. So in alphabet reduction, also like, okay, I won't be able to do it quickly. Like it will take at least 30 minutes to do this, even if I like quickly do it. So I will stop here, I think. Alphabet reduction is where Walsh-Hadamard encoding is used. Basically, you encode, so like you now have big cluster of constraints. Like each constraint is basically imposing constraints on a lot of other constraints as well, vertices as well. So you basically remember Walsh-Hadamard encoding maps it to a higher dimensional set, right? So you basically use it to somehow get back to the original alphabet set. Okay. So you define new alphabets, which are basically from the Walsh-Hadamard encoding of the graphs, like new vertices. And yeah, somehow you reduce the alphabet set using that. So I think you should read it yourself. I'll stop here. Does anyone have questions?